All right, welcome back everybody. This is our second video in Unit 5.11 for AP Calculus, solving optimization problems. In the last video, we looked at these first two examples and how we would do those. And in this video, we're going to work through one last example of using optimization in a familiar context. So here we go, example 3. A particle is traveling along the x-axis and its position, with origin at 0, can be modeled by x of t equals t cubed minus 15t squared plus 72t minus 9, where x is in centimeters and t is in seconds. Part A, on the interval from 3 to 9, find when the particle is farthest to the right. And it may not be instantly clear that this is an optimization problem, but again, optimization is fastest, slowest, highest, lowest, and in this case, farthest to the right. So when we're talking about position, farthest to the right is the maximum position on the time interval. So that's what we're looking for here. We're looking for a maximum position. And in order to get that, we're going to find our velocity function, which is the change in position, x prime of t. So we'll take the derivative of the function x of t. That gives us 3t squared minus 30t plus 72 as our function. We're going to set that equal to 0 and solve for t. Let's see, I can factor a 3 out of here. That's t squared minus 10t plus 24. And so we end up with, let's see, 0 equals 3 times t minus 4 times t minus 6. So x prime of t equals 0 at t equals 4 and t equals 6. Okay, so in the previous examples for optimization, I was using a sign chart a lot and finding relative minima maxima because we had open intervals, and so it's hard to do the candidates test when you don't have endpoints, or it's harder to do the candidates test when you don't have endpoints. But here what we're going to do is we're going to go ahead and use the candidates test since we're talking about this on the closed time interval from 3 to 9. Okay, so I'm going to set up my table for time and position. And so our time values, our left endpoint is 3, our critical points 4 and 6, and our right endpoint 9. And we're going to go ahead and substitute all of those into the position function to figure out which position is largest. So grab my calculator here. I'm going to go ahead and type my position function in here. And you can evaluate this however you please, whatever's easiest for you. I happen to like using this particular approach on my particular calculator. I'm going to type the function in, and then I'm going to figure it out for the various values. So it's 99 at time 3, and then at time 4, it's 103. And then at time 6, it's 99 again. And then at time 9, it is 153. And so, when is the particle furthest to the right? That's what we're trying to find. And so that's when the position is greatest, which is this entry right here. So the particle is farthest to the right. At time t equals 9. T equals 9 seconds. All right, so that takes care of the first part of this. By the way, for those of you who use like 83 or 84 models, in order to do something similar to what I did there when I was evaluating things, one thing that you could do is you could go ahead and type this function in your y equals screen. This is one of my favorite little tricks to use when I'm evaluating a function at a bunch of different places in my calculator. but I can go ahead and type this function in to my y equals, and then set up my table so that it is asking me for values. And then I'll go to my table and I can just enter these values in here. And boom, look at how quick that was to generate the table that we've got. So that's a way that we can do it on another model of calculator. All right, part B. On the same interval, what is the particle's maximum speed? Okay, so speed is the absolute value of velocity. So if we're trying to find the maximum speed, candidates for where that can occur are the critical points of velocity. So we find v prime of t by taking the derivative of our velocity function, and that gives us that v prime of t is 6t minus 30. So v prime of t equals 0 at t equals 5. That's our critical point, and so we want to evaluate the speed, which is the absolute value of velocity, at our endpoints and our critical point. 3, 5, 9. And so I'm going to go ahead and evaluate the absolute value. So I want absolute value of the velocity function, 3t squared minus, oops, what did I do? Oh, I forgot I switched calculators. 3t squared minus 30t plus 72, evaluated at t equals 3. Boom, that's 9. And then evaluated at t equals 5. Boom, that's 3. And then at t equals 9. Boom, that's 45. And now this time the question asks, what is the particle's maximum speed? So that's the optimal value here. Notice we didn't use the maximum position in part A, but in part B, our answer to the question is the maximum position, or the maximum speed in this case. And so the particle's maximum speed on the interval is 45 centimeters per second, because that's what speed would be measured in with the units that we're given. And there's our answer. And that's some optimization with particle motion there. All right, that brings us to the end of this video and the end of our lesson on solving optimization problems. You know how you get really good at solving optimization problems? You solve optimization problems. Because the hardest part of solving optimization problems is setting up all the various different models that we could possibly encounter. There are a litany of them, so many different ways that we could be solving optimization problems depending on the application. And so the more of them that we can encounter and kind of, get our feet wet as far as setting them up, the better it's going to be for us in the long term. So turn to your practice as much as you can, and hopefully you'll become great at optimization. All right, that's it for this video. See you all next time. Have a great rest of your day.